fine. It's probably
Yeah,
better that I
so
retook it
you
anyway.
write out the
Because I took time off before coming to school, and then I did take my college
checks
too,
on
so
the
sophomore
numbers,
year,
or
so that would have been like 2 years. instead of
simplify
that.
things a little bit there.
That would have been too much time.
That's fine. Good.
Be so mad if all my grades
It
were
was
lost.
my second take-home exam.
Horrible.
I
Having
forgot
to
to
do
write the,
everything. Yeah. You're like, well,
thing.
guess I don't
No
have a
word
degree
source.
anymore.
There we go, source. Yeah, the thing.
Yeah.
Hmm.
How are you liking biochem too? You don't?
I don't. I don't like biochem. I don't like Schroll's teaching. And I have to watch everything on Tigrides, so it's just
I love
terrible.
biochem too.
I think the material is interesting, and she just doesn't make me want to learn any of it.
It's one of my favorite classes.
No, it's my least favorite class. I like
I think
physics.
also the fact that like I was in the class also because it was like
Yeah, my class isn't
it was eight of us who know each other for like the entire college career. So
Yeah. Yes.
and because it was the second semester with the professor too, it was just like
Good enough?
Where's are you the senior or junior?
senior.
In both.
Yeah. Well, are you graduating this year?
No, I was supposed to, but I took an extra year.
Oh, okay. No, I was looking, I was gonna say something. And then I ended up having to drop my chem class because I wasn't doing hot in it, which is sad.
Which
but
one was it?
It was P-Chem 2.
I haven't taken that one.
See, I feel like
P-Chem
I
is a
love
hard
the
class,
professor,
I just
but like,
It was amazing. Cause I just didn't want it, but.
no, it was P-Chem like without, like they didn't, he was, oh God, is it okay?
I think.
I love that.
That's what happened.
Oh, a little bit of super glue enough to be fine.
A little less insulation, so.
We're gonna have 2 cups.
So, exam 2 is Wednesday in class. Monday we'll do some review. So some study material are posted, and this is one handout here about the material on the exam. So the exam will cover materials that's been on the 4 homework since the first exam. I'll focus on that. And in the stuff on exam, here, come up. Chapter 4 was some continuous distribution material, where it's maybe density, f of x, f of y. We might find the cumulative, the probability less than things under a simple one univariate. Maybe we take the expected value or find the variance. And we look at some specific ones, like a normal probability calculation or exponential as the primary ones there. So with some probability calculations related to that, and we find the means looking at graphs. In chapter 5, they started looking at bivariate distributions. They looked at distributions of 2 discrete variables or 2 continuous variables, but the exam will focus on the bivariate discrete ones, right? So that would be numbers in a table, and you could get the margins or the conditional or the means, or maybe the conditional means or covariance between those. So there's a little bit of doing with the tables and doing calculations there. In this chapter, there's a section on linear combinations of random variables, and we're going to focus on either the sum or the difference. We're going to restrict it to those two cases, and then the means either add or take a difference of the means. For the variance, if there's a covariance, then there's an extra term in there, and so that was a little bit more to deal with. The other important thing in there is this distribution of x bar, the sample average. So if x's are normal, then x bar also is normal. It's the same mean, but the variance is divided by n. Right? So the variance becomes more precise. In chapter 6, we didn't really go into too many details about chapter 6 because that was kind of introducing some ideas of mathematical statistics, unbiased estimation, minimum variance, and other things. That's more what's done in the 252 class, which is offered in the fall. So we didn't spend a lot of time there. You know, it's there's a few ideas. You know, it says point estimators. We're just going to use our data to get a particular estimate of that. Nothing's a random variable because it changes in random samples, right? So it has a standard error. So that was a big idea that came out of that. We also use Bootstrap to try to estimate that standard error. But we're not going to do more things with 6. There weren't homework questions on a lot of the other content. The big things that have been on recent homeworks have been confidence intervals and hypothesis tests, right? The chapters include quite a few variations in formula, and these things just exist. There's different ways people have figured out to do these things. We're going to focus on the ones that I talked about in class, that I represent on the solutions, and that are mentioned here. So you know, a confidence interval for a proportion. It gave a complex formula, but the simplified formula is the standard one that you can use. It's 7.11. For this, right, yeah, so I'll mention that shortly, right? There's a way to calculate the sample size, right? If you want to figure out what sample size you need for a certain amount of accuracy, that's a good formula. There's a confidence interval for a mean using a t-distribution. So that's one formula there. There's a hypothesis test for a mean, either just one variable or a paired one. It's actually in chapter 9, it's a paired one, but it looks exactly the same. Just take differences, and you're back to one column of differences. Or a large sample test for a proportion. And the last material we've been doing Monday and Wednesday really is a t-test for 2 means. I advocate that pooled procedure. You get to use the freedom as an integer, and it's a little more powerful if you can do that. Or 2 independent proportions, right? So the parameters that we could have is a mean, primarily with mostly these cases, right? So you get a mean, we get the sample standard deviation, we use a t-distribution, and figure that out. If we have 2 samples of mean difference and it's matched pairs, right? We take the standard deviation of the differences, and we use a t-distribution, and there's in sample cases, in pairs, or a proportion, or difference of means. I guess we also did difference of proportions, and I didn't quite put that one down there. But being able to do a confidence interval, hypothesis test, or a mean, or proportion, or 2 means, or 2 proportions, would be part of it. It'd be a little bit of interpretation. Now, I'm not going to ask you all versions of this. It's not going to be horrendously long, but it'll be kind of a 1 sample question and a 2 sample question and an interpretation, right, to make it. So there's some interpretation of the resultant context, some relationship between confidence interval hypothesis tests, right? So if the confidence interval, whatever the confidence interval says are likely values of the parameter, those things won't be rejected if you're testing, right? So if I give you a question, you know, is this a plausible value? I could leave it open. You could either do a confidence interval or a hypothesis test, but you don't have to do both. If you do one, that's sufficient to answer the question. So, yeah, so that's kind of an outline of things, right? So on this exam, you can bring in a sheet of notes. Right? So I think you can fit most of these formulas for the confidence interval and hypothesis test if you write them neatly onto just one page. Right? On the final, we'll probably expand it and let you use 2 sides or 2 pages, right? So you could write down the Z formula for testing proportions, or the confidence interval formula, have them there. Right? So you can work on putting those things together. You can write whatever you want. I will give you, as part of the normal table, the Z table, and the T table from our book. Right, so you get copies of those will be appended to the exam. Take those off and look up numbers on that. Right? So you don't have to write anything down there. If you want to write down special numbers for the normal, like 1.96 and a few of those things just to make it quicker, you're welcome to do that. But you'll get the full table. And you can write notes or numerical examples of different things. So that's what this file is, and the tables if you want to look at them. And these are some study problems. Mostly they're on the confidence interval hypothesis tests. So these things are the questions where I've just taken them from past exams in different courses that are relevant. And so there's some description of a problem, form a confidence interval, what do you conclude, and then some interpretation. And the way this is set up is that one part is a confidence interval version and one's a hypothesis test version, kind of with the same data. We can go over that on Monday, maybe some extra problems or extra question time. But one thing to think about as you look at that is how do you know which procedure to use? How do you know it's a means versus proportions? How do you know it's one sample versus two? Right? Is there, it mentions, like 95%, how does that translate into either a z-value or a t-value that you need to look at? Right? So looking at those clues and how it's written in there can help you identify what problem to do. If you write out your note sheet, at least a draft of it, before trying this, right, you can see, can I quickly identify which problem it is, fill in the numbers, get that numerical thing, to get most of the solution. Right? There's still some interpretation and checking and getting exactly what that's for. But if you can match it up based on what's there and what's in your formula sheet, you can get through some of those parts a little faster. So that's there. There's solutions. Some of the different homework assignments had extra practice problems. I've posted solutions to all of those except for this last homework. We'll get those done, and then after this homework is in, probably whether it's Monday morning or if anybody asks for an extension, on the homework, we'll see. But pretty soon the homework solutions will be posted for that one too. So you can look at the homework solutions, practice those problems. I look back through the homework solutions and the formulas in the book, right, when I'm making up that list, to try and figure out what to put on the exam to make it match what's in the class. Right? So I will be looking back at those, again as I write it, and the mix of questions. But any questions? So yes.
Can we make a chart for the formulas?
The whole chart for the formulas. Well, one thing to start out with, I might have something like that, but you could go through some of these different test procedures or the practice problems, right, or things in the homework and see what formula was needed for those, right? So you could put some time looking at the different things that have been done on the homeworks, and then we can talk about, do you need this formula or that formula? I don't have that right now, but we'll see. Get a little more detail. Yep.
How many questions are going to be?
Well, I haven't written it yet, but if it's 6 questions and you get the full hour, 5 minutes, it'd be kind of 10 minutes per question. Maybe each one has 2, maybe 3 parts. If it's 3 parts, maybe one would probably be more interpretation, writing a little bit. Sometimes I break the computations up into a couple pieces. I might find a standard error, and then do first part, state the hypotheses, and write something about what they mean. Step 2, calculate the statistic and report a conclusion. So yeah, 2 or 3 parts, 5 or 6 questions. But not. The goal would be to have time enough to finish and go back and look at answers and write some. So think about the parts that were. It took a little bit more thinking. The problems will be written on the page like last time. A couple parts per page where you can just write them in there. Calculator. Good to have a calculator. for that to write out solutions. Yeah, pen or pencil, fine. Yes.
So, are we gonna have a question session on Monday then?
Yes.
Okay,
Yep.
so, we can bring in anything, like, well,
Yeah, we can bring,
within
old,
reason.
past homeworks, other problems from the book. We can review formulas and, concentrate on what your question's about. Well, what I wanted to do today is it counts somewhat as review. So yeah, Monday. Review with questions. You're welcome to send me email questions as well. I have office hours Monday and Tuesday to do that. So, but today we want to talk a little bit about a bit about assumptions and how sometimes just the assumptions don't really hold. What do people do? And we're not going to do this completely. It's a broad topic. Chapter 15 in the book is devoted to things called non-parametric procedures and tests. There's a branch of statistics that deals with things, well, what happens when the data aren't normal and there are outliers and you have small samples and you don't want to use a normal distribution? What can you do to still compare distributions? We'll at least mention one or two things there, but we won't have time to really go into that. But in some fields it might be useful. So let's say we have some data, x1, x2, up to xn that are quantitative measurements, right? And we're interested in testing a hypothesis. Does the mean of the data equal some number versus the alternative that is not that number? Well, the T procedures, T-based approaches to this, or procedures, could either do a hypothesis test or do a confidence interval and compare it to that. If, in large sample sizes, the X-bar distribution is approximately normally distributed. And so we would do a confidence interval that would be X-bar minus some t-value, S over the square root of n, using the t instead of normal just for the fact that we're estimating the standard deviation instead of that. X-bar plus some t-value, S over the square root of n. And with these one samples, we used degrees of freedom minus 1. And we look at some confidence level like 95% confidence interval. And the idea of it being a parametric procedure is we're saying if the distribution is roughly normal, then a t distribution is going to describe our probabilities, and we can take that cutoff value very nicely there from a t distribution with n minus 1 degrees of freedom. And so for 95%, we're going to choose that multiplier there so that there's 2.5% in this tail and 2.5% in this tail, and we're going to get values up here. And for most values of the sample size, that's going to be somewhere around 2, 1.96 to a little bit more depending on the sample size. And there should, that would be the confidence interval. So if mu sub 0 is in there, it's not rejected. If it's outside of there, then mu sub 0 doesn't look too plausible. The other approach is a t-test. Right, so here's our test statistic. We take x bar minus mu sub 0. Right, compare our sample to that null value, and then divide by the standard error. And if the null hypothesis is true, and x bar is approximately normal because it's it's not too skewed to begin with, it doesn't have really huge outliers, and it's decent sample size. Right? Then under the null hypothesis, this t statistic in random samples should be distributed like a t-distribution with our n minus 1 degrees of freedom. So if our t statistic is unusual, if it's really big or really small, it's an unusual event. That happens when we're a long way from the null hypothesis relative to the standard error. So if we get a t statistic that's out past the cutoff, right, that's our reject where we reject. And those two things should give us the same conclusion about a mu sub 0. If mu sub 0 produces a t statistic out here, that means that it's more than that distance away from x bar, and it's going to be outside the interval, and so on. So there's that correspondence, right? But that assumes it's normal, right? And it's not, but in many cases you're going to get small sample sizes. If you have a big thing that you're testing that's expensive, you know, like the space shuttle engine or something, so you only can burn out so many of those in testing because they're billions of dollars, right? And so you test 5, and you get data that's kind of skewed, outliers, extreme. You know, using a t-test like this that assumes normality might not be too accurate, right? So what can you do? Right? Well, you can test something else. What can you do? If the assumptions, which is, you know, x bar are approximately normally distributed, is kind of at the core, but that's also, you know, related to n being large enough so that that's true. You know, the data x also, you know, not too skewed, and few big outliers, few extreme outliers. So if those type of things fail in some way, right, one alternative is to transform the data. We look at that at the end. Sometimes data that's really skewed by taking the logs or square roots can put it back on a scale that looks more symmetric. So things testing on that scale could be adequate for your purposes, and it will look much better. The other way is test in a different way. Some of these things are called non-parametric, that they don't require this large sample normality. Right? These non-parametric ones, sometimes they involve testing a different parameter than you started out with. But set things up in a certain way so that once you have your null hypothesis, the probabilities don't depend on, you know what the distribution is, it doesn't require an approximation, right? And so one example of this is called a sign test. And that's sign test for a median. So that's what we're going to look at first, right? So if, you know, so in an example, you know, we can think about really kind of paired, matched pairs data. And then I'm going to write it, you know, D1, D2, you know, Dn are little n, are n differences. So you say you have matched pairs, right? You have two groups, two possibilities, but each subject gets evaluated on each one. You know, x1 and y1 are the two measurements, x2 and y2 are the next two measurements, up to xn and yn are the next two measurements. And these are matched together, it's in subjects, get measured on both things. And we take the differences. DI is the difference between these two measurements. So our quantitative measurements, I switch between lower and uppercase. And I don't need to denote anything particular, so I'll just make them like this. Right? An interest could be whether the mean is 0. Right? So we could do our one sample matched pairs t-test. Say the average difference is 0 versus not. But if we have a small sample size, or it's really skewed, or there's some really big outliers, we might not be too happy with the t-test because of the assumptions. The alternative is called a sign. I'm going to run out of room again, so I'm going to put this on the next page. Right? So the sign test makes an assumption. Instead of saying that the mean difference is 0, it's going to say that the median difference is 0. Versus the median difference here is not 0. If the median is 0, what percent of our differences should be above 0? 50%, right? That's true no matter what the distribution of those differences was, whether it was normal or skew or had outliers or anything like that. So this assumption about the distribution, it's similar to saying the average is 0, but it's the median. So it's a different aspect of the distribution, a little bit different measure of the center. So this implies that the probability that a particular difference is greater than 0 should be 1/2. And we have n subjects being measured. And if p is the probability that a difference is greater than 0, is 1/2. What's the distribution of the number who actually are bigger than 1/2 if that null hypothesis is true? So if our measurement x now is the number of subjects with a difference greater than 0, if they're all independent subjects, there's n of them, there's a 50% chance that they're greater than 0, greater than the median. So under the null hypothesis, or assuming that's true, x is distributed as a binomial random variable with n pairs or n trials, so n, and the probability being 1/2. That's the distribution. There's no large sample distribution like it's approximately t or something like that. That's the probability, right? It's a hypothesis that creates a stricter situation. Right? So if we get a value, we observe x, say greater than the halfway point, we can calculate a tail area, a tail area probability, as the probability that x is greater than or equal to what we observe under the null hypothesis that p equals 1/2. That is, what is a p-value? A p-value is the probability we get something as extreme or more extreme than our data under the null hypothesis. If the null hypothesis says it's this binomial, and we've got something that's above average, above the midpoint, right, we can calculate the probability out there. And a p-value, well, for a two-sided hypothesis would be twice that tail area probability. And if that p-value is small, right, then we've seen something that's out in the tail of the distribution that's unusual, a long way away from 50%. So we reject null hypothesis if the p-value, right, is less than, say, 0.05 significance level, right? That's our standard. So it provides an alternate test here that doesn't actually depend on what those differences actually were. You can have a small number of them. You can have 8, 10, or 16, right, instead of 30, 40, 50. You have a small number. Some of those differences can be really big, really skewed, right? It doesn't have to follow a normal distribution. Whatever the distribution is x, this of the difference is underlying. Under that hypothesis, that's true for all of them. So the idea of this non-parametric thing is to set up a strict null hypothesis that specifies everything. In this case, the switch from the mean to the median ends up doing that. So let's look at how it goes in some example. Does everybody have a copy of the handout? So do you have a copy? You have a copy of this? You have this one? Oh, thank you. You have one of these? Yeah. Good. So imagine that you're testing versions of maple syrup. Right? You have 18 people, rate variety A and variety B, and 5 out of the 18 prefer variety A over variety B. That means that 13 out of 18 prefer the other way, assuming no ties. And so we could be asking the questions: are A and B, equal to each other in some sense? You could ask, do they have the equal mean if this is a quantitative rating? But if people just said preference or not, right, it's about a proportion essentially. So if they equal, the probability they prefer A would just be 1/2, and right. And we could calculate the probabilities that we would get 5 or fewer, since it's below the average probability. So the probability of almost, if it's really equal out of 18, the chance that you're going to get 0 is practically not going to happen. That's nearly 0. The chance for 1 is also small. 2, 3, there's some chance that you'd get 3 out of 18, or 4 out of 18, or 5 out of 18. This command gives all 5 probabilities together, and if you add those up, you get about 0.048. So if we had this scenario here, so we have 18 people doing ratings. These are the raters. We get 5 prefer A over B, right? So 13 prefer with no ties, B over A. Is A equivalent to B? They have the same preference, so they're really indistinguishable. So one way of phrasing this is saying that the probability that you're going to pick A is just going to be 1/2, and you expect it to be 50-50, right? That would be fair. Assumption about this probability, when we have 18, means that
9.
Sorry, what now?
So when you have 18, would the idea that B should be equal to 9, or are we seeing it's just like?
Yeah, it's or the number, right, that we would get. So if it was exactly balanced, if 9 preferred A, 9 preferred B, that'd be right at the middle, right? But we only got A. That, so we're calculating the probability that X is less than or equal to 5. The sum X then going from 0 up to 5 of the probability that we have that particular value. It's binomial probability, so that's not something that's going to be asked on this exam. You won't need to repeat the binomial formula. We did that on the last one, discrete variables are there. But that binomial formula would be m choose x, 1/2 to the x and 1/2, so it's just 1/2 to the n, but that's the probability. And in this case, right, with 18 and 5, it ended up being 0.048. 0.048. Which is a little bit less than 5%, right? But that's only one side. You know, if we're just asking is it equal versus not equal, right, we probably would double that for a p-value. So two-sided things over here. 2 times 0.048, 0.96 as something. If you're doing two-sided, do these 18, the evidence based on these 18 people really show that B is preferred and A is inferior? Has it really demonstrated that they're not equal? Well, 10% significance. This is not quite convincing. Right? If that were a much smaller probability, like if we have just 4 or 3 and taken out most of this probability here, right? If we got 0, 1, 2, 3, something like that, or 4 maybe, then the p-value is going to be smaller, but 5 is just not quite enough. So this is a little bit bigger than, this is bigger than 0.05, and so we do not reject H0, the probability of preferring A being 1/2, although it's not looking too good for it because of the people seem to prefer B. It's not statistically significant yet. Sample size is pretty small, it doesn't quite cut it. Yeah.
I know that the social sciences, they usually have a higher p-value of like 0.1 because of the fact that humans are, well, not easily
Well, it depends.
not always normal. So if like you had that higher p-value because of the fact that you're just surveying people, really.
Well, you know, it's that can be kind of a different consideration, right? So you could have something that's very noisy and has a lot of variance to it, like human traits or behaviors, right? It's hard to predict what's related to what, right? And so I think about these different standards, right? It's kind of like an alpha level 0.05 kind of as a starting point. Most things are going to be significant if it's less than 0.05 and not significant if it's bigger than. I'd rather have the p-value itself so I can see what it is. And I can know, is it 0.06, 0.04, or versus 0.001 versus 0.25. I mean, there's a big difference between those. In some research, things are more exploratory. So you're gathering small samples, you're doing testing. Well, you know you're not going to, don't have a lot of power to get significant results, right? Genetics, sometimes it's done this way. You have 40,000 genes that you can type in a machine, or 100,000. Now, the whole genome, right? And you're testing them, are they related to some diseases? But you only have 20 people in your sample because it's expensive. So you know that, and if you're just kind of exploring, you don't have a lot of good biological hypotheses. You might let things go through and be classified as significant at like an alpha 0.10. So more things are able to pass that threshold because they don't have to be as extreme to be p-values less than that. Right? And so this would let more things go through, but it's probably not the final proof. So you're kind of generating hypotheses, what's possibly related to this, what should we spend our time looking at in the lab to see if it's related. Right? You might be testing on an initial sample like this. On the other hand, if you've seen a lot of evidence about something, and now you just want to really, make sure you've done a power calculation, you think that there's a big effect size, and you want to prove it once and for all, you might require, a little bit more stringent evidence. So kind of in that range, 0.05 kind of being the typical thing to get through. But you know, more important than the exact cutoff level really is communication. What are the estimates? What are you comparing it to? Did you clearly set up hypotheses before you did the study, before you kind of exploring and generating them based on looking at the data? Right? It's more powerful, more meaningful if you could set up clear scientific hypotheses and then confirm them. And then at what stage of your research? Are you doing new research on a new emerging phenomenon, kind of exploratory? You might not want to throw everything out as not significant, but especially in small sample sizes. You give a lot of power and you really believe it, and you confirm it, 0.05 or a strict, more strict is good. Yeah. Show me the estimates, show me the graphs, show me the p-values so I know exactly what's going on.
I still want to know who's funding all of these interesting studies. Like,
right. So, yeah. So one place to look for funding, National Institutes of Health, right? Grants and funding. They have billions of dollars of funding every year.
but like,
And
typically, like homework examples have been things like, oh, like how much toothpaste is left after you squeeze it out?
well, National Science Foundation also has big funding for scientific research. I mean, another big funder is foundations, like Robert Wood Johnson Foundation, Bill and Melinda Gates Foundation. They're spending millions or billions of dollars to fund research projects. And then there's industry, right? So if you're making toothpaste and you are producing these things and you're producing them at the rate of millions of units per month or week, right? And you can make a little tweak in the production process to make it faster, to make the chemical mixture work better, be more appealing, in some way. And, you should spend at least a little bit of money on experiments, right? To try and make things better. And with a good design, you can make kind of continual improvements in there. So industry would be funding some of these things that might seem a little less scientific, right? They're scientific in a way, but it's more marketing of very applied things, not necessarily getting at the deeper science of things. One example, we use that example with the paired data with taking people to a museum and having them examine museum objects and get that experience, and did that seem to improve their health, right? That in the newspaper, in the Burlington Press, in the Free Press, the day kind of after that, or around that time, was a story about the benefits of patients in hospitals getting exposure to plants. So there's groups that think, that patients should have a humane experience, it shouldn't be all drab and gray, that there should be things like that. And so there's organizations like that have, legitimate ideas that they think that things can be improved. But to put plants in hospitals is expensive, right? I mean, if we had plants in each of these rooms and somebody had to water them and clean up after them and, pick them up when they spilled and replace the dead, so it's an expense. So does it make things significantly better in some way? Does it reduce their feelings of pain? Does it make them feel happier? Does it reduce the time that they're in the hospital for longer term care, right? If it has any measurable benefit, right, then maybe you could argue that it's worth doing. So I found one article, so patients for plants, so plants for patients. Just generally search for that. There was one of these that was I don't see it right now, but there's literature, there's Journal of Horticulture, there's different holistic care journals, and they do research on stuff like that. So.
Like, I know that there's a movement in hospitals to actually increase colorfulness of the rooms because of making it more appealing for people to stay there.
Yep.
Because they are businesses in a way as well, so you kind of
they're
want
big
people
businesses, yeah.
to choose your hospital because it's the one with the prettier room. I don't know.
Right.
I don't know what their like logic is, but
Right, well, I mean, so, people are complex, right? And so there's likely is something to a placebo effect. If you have a good mental attitude and think you're going to get well, and this is going to help you, it's our bodies do respond to negative and positive experiences, emotions, and things like that. So there's likely something to it, right? And part of it is, our brains do produce chemicals depending on how we feel, right? So we're complex, and some things like that do affect mood. It's could really have a benefit, but it also could have an effect on, from their business side, if their relatives and caregivers are rating the hospital based on their experience, and they said, "Oh, it's nice in here," then there could be that. That's more kind of a business. I don't know if it's a cynical side, not just health, but just ratings, but there's an element to that. So in this case, there's also a binomial test. Getting back to this, that will do what's called an exact binomial test. That's adding up the binomial probabilities. So if we had 5, and the data was 18 trials, it reports a p-value of 0.0696, which is about what we calculated there. It gives a confidence interval for the probabilities. It does include 0.5, so maybe they're equal. It certainly is weighted toward one side, so this type of non-parametric test, is common. What happens though if, say, we increase it to 5 times the sample size? If you had 25 people out of 70 prefer A, so that same rate of 5 out of 18 multiplied by 5, if that same rate continued but a bigger sample size, what do we see? The binomial test there then gives us a p-value, two-sided p-value that's about 0.02. If we had 70 people and only 25 of them preferred A and then 45 preferred B, it would be significant. Yeah.
Wouldn't this be a different ratio? Because, so 5 times 5 is 25, but 18 times 5 is 90.
Oh, okay. So it's a different ratio. It's actually, this is actually closer to 0.5. Yeah, right. I didn't exactly multiply by 5. You're right. Yeah. So the probability, the point estimate is 0.35. Before it was less. But this one's significant, right? This confidence interval, based on a proportion, doesn't include that. The effect of the sample size, is big enough that even though it's moved closer to 0.5, it's still significantly different. On contrast, if we had different scores, let's say we had these 8 scores here, this D1. These values of D1 here, here's the D1 values. If we had a small sample size, what do we see in these data? One person really, you can imagine them rating on a 10-point scale. Score A on 1 to 10, score B on 1 to 10, and we're going to take the difference of those scores. Somebody really didn't like A and really loved B, right? Somebody, that -8 there would be a big difference.
they found a native Vermonter.
Maybe, yeah, somebody, or Vermonter,
Like an
or
old
somebody
type
from
Vermonter.
Quebec, or something, right? You can do a t-test with these type of things. So, in these data, there's 2 out of 1, 2, 3, 4, 5. I guess 2 out of, what's the length of? It's not exactly comparable, right? It's 7. It's 2 out of 7. The binomial test. If you do that sign test there, where there's 2 and 7, the p-value is not significant there in any way. But you technically can run this t-test there and get it will give you all these things, but it's based on only 7 observations, and some of those, and at least one of those is pretty skewed, right? That -8 is a lot different from that. So you could imagine somebody wanting to summarize, if that's all the data you had from real small samples, you want to summarize this and report like a comparison, a conclusion. If you did both the t-test and the non-parametric one, the sign test, is it above or below the median, and they're consistent, that's better. It's one's testing the mean, one testing the median, but if they both say there's no difference, or they both say there is a difference, right, it supports what you're doing. If they come out different, well, then that outlier or the small sample size kind of puts a little question into you might not want to go out claiming to the world that you've clearly proven something. You might want to be a little more cautious. Right? Science is a little cautious in terms of that, right? If there's more, what happens with this one? That difference, this difference would be almost significant. The binomial test, this had 1, 2, that was the other one. This binomial test, if it was implemented that way, right? Oops, I highlighted that 0, so it should be 0. So in this D2 one, where you got 16 out of 20 being one-sided, that got a p-value that's 0.01. Right? But if you look at the differences, the t-test based on these things, it wasn't quite significant. So this is the t-test of those 20. Right? V2, the V2 numbers are here. If I sort those, you get these numbers. Again, that -8 kind of looks like an outlier. I can do like a stem and leaf plot, maybe. It's hard to see that. That one kind of looks like an outlier, fairly small sample size. You can get different results by using these different methods. In terms of good, honest communication, I would say report both. And we tested it this way, and we did also the sign test. The sign test was significant. The t-test wasn't, but there was this one big outlier out there. If there's one really extreme point, some people might take that point out and redo the test. Of course, you should hide that and say, I only have 19 points, and look how significant it is. Right? You should really look at, say you took one out if you took it out. Perhaps this one you might worry that it's coded wrong, that really the E first is an A and it should have been an 8. You hypothesize about that, but unless you actually know how the experiment was done, you wouldn't really be able to make any conclusions related to that. Right? Just to mention, we won't go into other details in particular, but there are other procedures that are based on based on the ranks of the data instead of the actual numbers. There's something called a sign rank test. And again, this is a situation where you can form a hypothesis about your data expressed in terms of the ranks. It's not exactly the same saying that averages are differences, but saying something about how the magnitude positive or magnitude negative about the data is the same. So what is a rank? So if we have data x1, let's do the differences. In this example, d1, d2, d3, up to d sub n. If you put the rank of these data will be what position the difference would be in if you put it in ascending order. Right? So the smallest value gets rank 1, the biggest value gets rank 2, and the ranks, no matter what the original distribution of x was, are going to be the numbers 1, 2, 3, up to n. Not necessarily in that order, right, of the data, but they're the numbers 1 through n. They don't have any low outliers, they don't have any high outliers. Right? And if these distributions are the same, if the distribution of differences is symmetric about 0. So you have some differences below, some differences above. You rank them all. Well, those would be the ranks. Then the sum of the ranks of absolute differences should be the same. So absolute differences, we're going to take the absolute value of each of these. So kind of take the negative and positive and fold them over onto each other, and then look at the ranks. But anyway, there's a test based on that says, are these two distributions the same? Because the ranks are ranks, they're 1 through n, under the hypothesis that they're symmetric. Half of the sum should be on one side, half the sum should be on the other side, and it doesn't matter whether they're skewed or not, right? So it's a strict hypothesis. Yeah.
Isn't that similar to the median, in that just kind of looking at one half and the other?
Yep,
Or-
yeah, so it's
or
kind of
is-
looking at, it's something that's constant across all distributions, right? That the median is the 50% point no matter what the distribution actually was, and under the assumption that there's just some symmetry, and that it's kind of equally big or equally small above or below. It doesn't matter if there's a long tail or it's skew or anything, you know what matters if it's skew, right? So, but that just as a difference. So this signed rank test also is possible to do, and I don't have. The last thing I wanted to just show you just a little bit about these transformations, right? So there's a bunch of data sets in R on all different sorts of things, and there's one that has areas of, where'd that go? Of islands. And these different islands, in terms of the area, is extremely skewed. Right? Most of them are here, just a few points, but there's some of these extreme ones. So even though there's a fairly decent sample size, above 60 or so of these islands, if you do distributions based on the mean, the sampling distribution is still going to be skewed. Averaging together 60 things when it's that skewed doesn't overcome that. But things that are on the islands or in areas, there's kind of tens, hundreds, thousands, kind of multiples like that. If you do the logs of the areas and do a histogram, it's not as extreme. It's still skewed, but it's not as much. So it's very possible that the averages on the log scale, if you did t-tests based on average on the log scale of their sizes or their lengths, things would be better. There's another one called rivers. It's the length of the longest rivers in the United States. So the Mississippi, the Missouri, Colorado, or some of those big ones out there. Right? But again, it's pretty skewed. Take the top one. It's not really a sample. It's really just the biggest one. But if you had a sample like that, taking the log of these, produces a distribution that's pretty normal. So if you wanted to do a confidence interval for the average length on a log scale, t-procedures would work quite well. There's a data set that's on the 50 states, and many things are, like population by state is extremely skewed, but taking the square root of that, or maybe the log of that, produces distributions that are not nearly as skewed. Right? So here's the original one. California, New York, a few others, Illinois, very large, Florida have very large populations, but a lot of us like in Vermont or down here, Vermont's kind of near the very end. But, an area of states. Then we know where the largest state.
Alaska.
And Alaska is up there, and Texas, and California, right? But it's, you know, if these were a sample from some population, like a sample of counties, and some were enormous, you know, doing anything, you know, could do things on the square root, or on the log scale, makes it, you know, it doesn't necessarily look normal, but it's not as skewed. So taking samples from this will work much better. So, but anyway, if things are not quite normal or don't look at the assumptions, there's ways to go about it. We're not stuck with anything, but sometimes you have to change the data, transformation, phrase it on a different scale, or ask about a different parameter like the median, that then tells you more about the probability. Okay, so Monday we'll answer, you know, bring your questions. We'll go through some problems. We can use formulas, numbers, make up new things to address whatever you have questions about.
Can I just ask a quick question? I was just looking through the little, for a review.
Thank you.
One of the questions I saw in the homework though was the whole, this B here. And just don't understand what it's asking. He was talking about, like, you know, MS talks with that it's equals 10% less, or are you saying?
So that's kind of asking about how. So I'm really asking, you know, what's the probability that you reject?
Alright, so that's just power, and then you do the same thing for 200%?
Yeah, so we haven't, so for in terms of the test and things, I think it's one of the practice problems, whether, yeah, that.
I saw it on the actual problem.
Yeah, I was like,
Yeah.
right?
What? No.
You're just bad.
No, I just
Believe it or not,
really
I'm
bad
very
reaction.
actually helping notice more, so
Yeah.
I don't mind keeps my mind on that side,
Just
but
like wandering
get really
away.
Sure.
so lazy. I was just looking at the end, I'm like, wait a minute, I don't, all that stuff question is asking, which is what, okay, so it has to do with power?
You find where you reject in all hypothesis, and then find the probability that you're under that, if it's that extra, if it's a value value.
Emily's not here to walk me back to my house, but it's okay because it's different alleys walking. I was joking with her
Anyway,
yesterday.
Thank you. Are you going to request,
Yeah.
schedule that?
Yeah,
Sure.
oh, actually, no, for the exam?
Yes.
Actually, I learned we're not leaving until 3, so that should be fine.
Okay.
I'll
So you-
just, I'm just gonna talk, I'm scheduling it with,
Leslie.
Leslie.
Good.
No, it's okay, but I should have.
Great.
Can I swing by your office at 3?
We have a faculty assembly, so I'm going to be
No.
over there at that.
Usually there is one.
But if you're-
No,
but if you're
there's
bringing
no
in the
You have
homework,
me
you
like,
can decide it at that
3
time.
times this
Okay,
weekend?
I just have a question on.
Study. For study, but I was also thinking about the whole formula sheet, if I need to do that too.
Why don't you hand in the other card, yeah, and I could send,
Grandma's 90th.
you know, a request, you
So
know,
we're going to New Hampshire.
Nice.
summary.
I don't even know when I'll be studying.
you know, kind of generally how to approach the problem, and then,
Me too. It's okay. Gotta go put this
Wait.
in my
Don't forget your
I know
phone.
you're gonna ask Leslie for an exam time.
Yes, I already did.
Okay, good. I'm sure I'll get up with her soon, so.
Yeah, but then if I have any questions, I don't know what you want me to do.
You know, you know, approach to taking the test is to write down, you know, as much as you can, you know, it'll be means, proportions, these type of things. So identify the parts of the problem, write what you think the problem, you know, is about, or your assumptions, like you say, I assume this is about this type of problem, here's the formula I would use for that problem, and then do the problem consistently under those assumptions, you can get some points for that.
Yeah, but what if I have questions?
I know, well, that, I don't know that I can, you know, I'm gonna be giving the test in here.
Yeah.
So, you know, that's just a difficulty of this.
Well, what I have done in other classes
Yeah.
is I sit in class, take it with everyone else, and then when the class is over, I move to the library for
Oh,
the extra
okay.
time.
Well,
That way I could look at the questions and ask you while I'm here.
Yeah,
and then-
no, that's a good suggestion, I like
Yeah.
that, yeah.
And
So
then I could-
that's fine with me. so.
Okay, all right, so I'll let Leslie know.
Okay. Yep.
Bye, thank you.
All right, thanks.
And I'm working on the homework. I will get them to you, I promise.
Okay, thank you, Kira.
I'm so sorry. I'm just horrible this year. But yeah.
And senior year, you'll.
I've been
get it
working on
done.
them. I've been chipping away slowly.
Good.
I'm grounding myself to like make it so I could